y. So we'll take a look at the y's that you had questions about. So we'll take a look at our first one on the left. 120 decimal point. Okay? So in my analysis, what I would always go through and do is underline my significant digits. So 1 and 2 are always significant because they match rule number 1. Digits 1 through 9, always significant. Okay? The next part is deciding, is the 0 significant? Okay? To decide that, I have to look for a decimal point. Okay? There is a decimal point, so I'll use rule number 3. Okay? If there is a decimal point, then the 0 needs to be immediately preceded by means in front of it, okay, to the left of it, a significant digit. So I'll start at my 0 and I move immediately to the left. What is there? 2 is not a bad idea, but I think we can do better than saying 2. It's a significant digit. If that is a significant digit, then what does that mean the 0 is? Significant. And I have 3 sig figs. That's how it applies. Right? I know we didn't circle it, but we have virtually the same number right above it. Why is that one only 2, not 3? Without the decimal point, the rules change. Right, without the decimal point, I have to have a sig fig both to the left and to the right. And if I look to the left of that 0 above, yeah, I have a sig fig, but what happens when I look to the right? No. There is no significant digit, which means that 0 is not significant. I only have the 1 and the 2 being sig figs. David first, then I'll go to Bianca.
And how come the bottom right one, that 0 is significant to the very right?
Okay, so we want to jump to the bottom right now?
Yeah.
Okay, so let's move to the bottom right. Okay, same idea, we need to go through and underline our sig figs. The 1 and the 2 are significant digits. Okay, I do have a decimal point, so I will follow rule number 3 again. For the 0 to be significant, it must be preceded by, immediately to the left, a significant digit. So I'll start at the first 0 and I move to the left. What's out there? Nothing. What does that mean?
It's not significant.
Not significant. I move to the next 0. I look to the left. What do I have?
A 0. Not significant.
We have not a significant digit, okay, which means also not significant. I move to the last 0, move to its immediate left. What do I have? A significant digit, which means
It's significant.
that 0 is significant, and I get 3 sig figs. Okay. So where you might be thinking is, well, leading zeros versus trailing zeros, which I don't know if the textbook does that or not, but that's a horrible way to look at it. There isn't leading zeros and trailing zeros, and because then you say, well, sometimes they're significant, sometimes they aren't. No, it comes back to these rules. Look at your decimal point and apply. The zeros in front of, I'll get to you, the zeros in front of our bottom right, okay, there's no significant digit in front. We look at the 0 at the very end, there is a significant digit. Those zeros have different meanings. If we move to the 120, no decimal point. Okay.
So that's
This one had a decimal point, different rule set. The 120, no decimal point, I have to have a significant digit to the left and to the right. It's a different rule set.
I got you.
Okay? So that means that 0 is not significant. Does that work?
Yeah.
Bianca first. Did you still have your question?
No, I don't.
Okay.
So if there is like a number in front of that 0 to the far left, then all those zeros in the middle would become significant.
So I believe what you're asking is if we take a look at that bottom right, and we tweak that number and make it a 6. Now how many sig figs do we have?
6.
Okay. Well, the 6 is significant, the 1 is significant, the 2 is significant. I have a decimal point, so I look immediately to the left. Significant digit. Look immediately to the left. Significant digit. Look immediately to the left. Significant digit. So we end up with 6 sig figs. Okay. Bottom left, we have 4 sig figs for similar reasons that we just did by making that a 6. Okay. We have a decimal point, which means with the decimal point, we just need a sig fig to the left. The 1 and the 2 are significant. I move from my 0 over. I have a 2. That is a significant digit, so that 0 is significant. that 0 is significant, and end up with 4 sig figs. Make sense? The last one that's circled, why do we have only 2 sig figs? Why do those zeros not count? Well, again, decimal point, because that decimal point, I must have a sig fig immediately to the left of my 0. So the very first 0, what is immediately to the left of it? Nothing, which means that 0 is not significant. I move to the next 0, what's immediately to the left of it? An insignificant digit, which means not significant. The 1 and the 2 are the only significant ones. Okay, move through that kind of fast, yes?
So if it was 1.012.
Let's try that again. You said if it was 1.012,
Yeah.
how many sig figs would it have? Well, the 1 is significant, 2 is significant. I have a decimal point, so with a decimal point, I just have to look to the left of my 0. What is to the left of my 0? A significant digit, which means 0 is significant. And that one now has 4 sig figs. Seems kind of like you guys got it. Okay. You just need to know the rules. You have to apply the rules. Period. Okay. I want to draw your attention to one last case. What's the difference between the two numbers shown? There's a 0 showing up in 1, right? Yeah. Right? Is the meaning different?
Doesn't matter since it's insignificant.
They both have 2 significant digits. The 0 that we're adding there is insignificant, right?
Shouldn't be any different.
So they're both correct. The top one, if you write it in your lab, you will usually see me circle it and write LZ.
It's lazy.
If I'm feeling particularly irritating, I might say like -20. Okay? What is the LZ? And everybody says lazy. I clearly need to increase my vocabulary.
That'd be funny, because you said LZ for lazy, if it was, and then you're lazy to write lazy.
Yeah. No, it's not lazy.
It just goes against her.
Lost to 0.
Lost to 0, that's not a bad idea. Okay. It's leading 0. Why do I need to write a leading 0? What number did I just write? What is right there? I know the screen's kind of dark.
Decimal point.
What number did I actually write?
0.12.
0.12. You all said the answer was 12. Nope, it was 0.12. I wrote 0.12. You interpreted that to be 12. What if I had instead written, why the hell did you write a 0 in front of 12? That doesn't make any sense. Oh, I bet you put a 0 in front of the 12 because it's not 12. I put the 0 in front of a decimal point that I didn't see. Oh yeah, I look a little bit closer, there it is. By including that 0, you've now added a break in your brain that you will look for that decimal. Without the 0, maybe your decimal point isn't obvious and your number went from being 0.12 to 12. That's a pretty huge difference. The 0 is there as just a marker to say, hey, watch out, there should be a decimal point there. Right? For those of you who think that you aren't going to make that mistake, you usually do, and you usually make that mistake on the exam. Okay? 2 ways to get around that: make a really big 0, make a really big decimal point. Okay? This is why some countries don't use decimal points to mean decimal points. What do they use? They use commas, because the comma now calls attention to there being something there. It's harder to just hit and draw a comma. If we draw a comma, there's now a definitive line there. It stands out a little bit clearer as the decimal point. Okay? There might be some other reason behind it, but this works nicely.
Because you would use decimals for like thousands place.
I don't understand the full theory, so that's what they use? Yeah, okay. So they trade commas and decimal points. Okay. And yeah, that's going to be entirely foreign to us. That doesn't make any sense, but that's what they do. Okay. Why they do it is a separate issue.
They probably did it first and we changed it.
Yeah, I'm sure we came up with something stupid because we could be better. Okay. So, next one. Measurement versus exact. Okay. There are some measurements that don't require an instrument. How many quarters are in that picture? 7. How many sig figs in that observation? Okay. So if you're saying it's 1 sig fig, then I could also go through and say, well, I'm going to guess 7.1. Are there 7.1 quarters there? No, there's 7. So 7.1 is wrong, right? Okay, so how do I fix that? It's not 7.1, it's
7.0.
7.0. Okay, well, I'm going to say it's 7.01. No, that's still wrong. Okay. Okay, so I heard put the hat on it. Okay, we give it a little hat to say that we run that 0 out. Sure. Okay, now how many sig figs are there, though? This is actually where it comes in. When we have an exact measurement, okay, we have infinite sig figs. This usually works with things that are we can count, usually 20 or lower, because we all have roughly 20 digits, fingers and toes. So we can reliably make that count. And those will be our consistent, observed, infinite sig figs. Where does this become important? Okay, let's see if I got better as an animator here. Oof, it got worse. Oh, it got much worse. What do we have? A foot! There we go, thank you. As long as one person gets this right, that's all we need.
What kind of toe is that? Like, look at that big
It's like a
toe.
moose head.
We have 1 foot. How many inches are in that foot? 12 inches. How many sig figs in that measurement? I heard 2 sig figs in that measurement. How many sig figs in 1 foot? That says 1, but you're now telling me it's 2? Well, I say there's only 1 sig fig in 1 foot. How many sig figs in this? I think I heard you say it, Michael.
No, I
Said something else? Okay. It's infinite. This is a definition. There are exactly 12 inches in 1 foot. This conversion has infinite sig figs because we've defined that to be the case. Okay? So there are certain situations when you look at a number, you might say, well, that only has 1 sig fig. 1 foot is not 1 sig fig. It is an infinite number of sig figs because it's not a measurement, it's a definition. Okay? So you have to be careful when you're looking at your relationships to make sure that what you're defining or what you're looking at are either measurements with certain numbers of sig figs or exact values. Okay? Exact values carry infinite sig figs. Measurements carry the sig figs that are defined.
We'll say that a foot was 12.2 inches instead of 12 inches. Would it still have infinite significance?
If we now
That's
change
exact
the
measurement.
definition, okay, so we can run this for a different system. See if you guys know this one. 1 inch is how many centimeters? 2.54. How many sig figs in that system now?
Like I would want to say 3, but
You would want to say 3 because you've got 2.54. Well, you didn't say 1, so now we'll just say, let's just evaluate that at 2.54. Okay? What comes after that 4?
I'm sure that you get some whatever detail.
Nothing smaller.
Nothing comes after that 0 or after that 4. Literally nothing. Because what has happened? This conversion is the standard conversion between English and the metric, or American and the metric system. Okay? And it gets converted so frequently that we sat down and we said, okay, we're never going to agree to completely convert to the metric system. We're never going to agree to completely convert to the American system. So we're now just going to agree to disagree, and we're going to define the relationship between inches and centimeters as 1 inch is exactly 2.54 centimeters. It is a definition, which means how many sig figs are there? infinite sig figs.
So technically, like large scale, super large scale, super small scale, super large scale, there could be an error technically when you do those like large scale.
When we're looking at our conversions, we will, particularly when we're moving between metric system, metric and English, we will find that you can introduce an error depending on how you solve your conversion. Yes, but we aren't going to cross that bridge yet. We'll probably cross that on Thursday. Okay, but we will see that happen. Okay? This is one of the reasons why we have massive issues between converting between systems. Okay? And why we don't work very well together with other countries trying to build a centralized thing. Because we can't communicate properly our devices in that sense. Okay? So exact measurements. The fuss over the sig figs really is going to come down to this next part, our operations that we do with them. When you're in the lab, you don't worry about sig figs because you're taking a measurement. You report what the instrument tells you. That's it. You use it. You move on. Okay? The issue is in the lecture, you aren't taking a measurement. You are taking a measurement that I'm giving you. You have to be able to interpret the sig figs off of that measurement to be able to do any kind of analysis afterwards. So if we go through and do this simple calculation here, the addition of those three numbers. Okay. I'm a little bit rusty with my addition, but I think I can pull this one off. I think it's going to come out to be 115. Yep, I'm really good, and I can actually add this the reverse standard direction, right? You usually add at the end. Okay? And we'd get that for an answer. That's what our calculator spits out. And yet, if you tell me that is your correct answer, you're wrong. What is the correct answer?
15.7346.
The correct answer is 115.6. Brian. Okay. Well, why?
Do you round like all the time, or is it some kind of
Right? The y is actually already on there. When we add and subtract, our answer is only as precise as the least precise place. So we take a look at all of the measurements that are reported here. Which of those is the least precise? 114.3 is only precise to the tenths place. All the other ones, differing numbers, but go out to further decimals. Okay? That means when I do the addition, I can only report out to the tenths place. Yes, I still have to run all the addition out on that because those other numbers could have potentially affected that. Okay? But I can only report the accuracy of my answer to the tenths place, and I get 115.6. I do not ignore the 5.2 in the second number, and I do not ignore the 8162 in the last number. Okay, they still get added into this, but I can only report my answer to that 6. Okay, Braxton.
For some reason, I'm very confused because I've just taken the least amount of sig figs and used that.
That's an interesting question. We'll deal with that in a second. Okay, and by a second, probably give me a minute, 2 minutes. Okay. Why do we do this? Okay. Why did I not just report 115.63362? To get that answer, what am I doing? I am assuming that that top number is actually all zeros across. And the next number is zeros there. Do I have that information? No. Those could be zeros. They could also be 9s. Okay. Why did I pick 9s? Because that's going to show the biggest differential. Okay. Since you guys were smart enough to look at my fine print, if we go through and use the 9s, the number comes out to be 115.7346 as opposed to 115.63362. Okay. Do we now have a difference?
Yes.
In that tenths place, we have a difference. That's where we vary. It's in that tenths place. That's where the error is, because the tenths place is my guess. Okay? That's the precision of my measurement now. is dependent all back on that place. If I report any number after that guess decimal, it's a guess on a guess, everything's wrong. Kind of make sense? Okay. Braxton put forth the question that he said, well, what I remembered was that it's all based off of the fewest number of SigFigs. Right? Well, it's not that he's wrong per se, it's that he's wrong in this circumstance. When we do addition and subtraction, it's based off of the precision. Okay? It's the least precise place. So I have to look at the least precise decimal value. But what happens if I do another mathematical operation, such as multiplication and division? Now what changes? Well, look at the rule. Our result is only as precise as the measurement with the fewest SigFigs. Now what Braxton's remembered is valid. Okay? And we go through and we can run the same idea. To get the area of the square, what do I have to do? Multiply the two by each other. Right? If we went through and did that, we'd get 33.488. The answer that we would have to report would then be what? 33. Okay? Not 35. Okay? That 4 does not make it closer to 35, okay, or 34. Okay? If we said 33.5, we now have 3 SigFigs, not 2. Okay, so we can only say 33. Again, why? We're making the assumption when we enter that into the calculator that the rest of or the next digit past that 6 is a 0. Okay? It could have just as easily been a 9. And if it's a 9, what happens to my answer? It changes. Okay? I get a 34 versus a 33. Okay? Those are our significant differences. We're looking at where that error comes into play. Okay?
If it was 4.69.
We'll deal with that too.
Oh, okay.
Okay? Whoops. Our error comes into play in the ones place. That's why we can only report out to the ones place. Because we're doing a different mathematical operation, the error propagates through your calculation differently, which is why you have different rule sets. One for addition, subtraction, one for multiplication, division. Make sense? Okay. What if rounding? Take a look at our addition, subtraction. What's our answer? How many SigFigs do we... no, let's just say what's our answer. So 1, yeah? 0.3, and I'm hearing we want to say a digit for that next one. But you said 4, not 3. We look at the first insignificant digit in our calculation, and we compare that and see where that is. Okay, 5 is dead in the middle, so we're halfway between 1.33 and 1.34. Okay, so it is literally a coin toss on deciding which way we go. Okay.
I thought 5 you always round up.
Yeah, 5 you do.
Always round up is unfortunately a vague term. Okay. Depending on the system used, you might always round up, you might not. Okay. It depends, unfortunately, on instructors, it depends on courses, it depends on where you were trained in which country. Okay. For the most part, if it is 5, we do round up. So with that being a 5, I then add 1 to the previous place, and the answer becomes 1.34. That's how I would round. Make sense? How about with the multiplication division? What's my answer?
36, 37.
So I'm only allowed 2 SigFigs. So the 3 and the 6. So I look at my first insignificant digit, which is a 5. What does that mean? I add 1 to the previous location. My answer becomes 37 units squared.
I might have missed the part where you explained it, or I don't know what happened, I just missed it. Why do you add 1 exactly?
It's our
is it
rounding.
Because you're rounding
It's
up?
just our rounding, yep.
Okay.
5, by definition, we round up.
1 would be a situation that you round down.
1, 2, 3, or 4.
Okay, that's safe.
Yeah.
Yes.
And what's rounding down?
You kind of made it seem like there would be a situation where if there
Well,
was a 5, you could
it
still
wouldn't
round
be,
down.
you wouldn't be rounding down, you would just keep it at 36.
You're just messing with me at this point.
He was saying like,
Okay, with prices like.
In other countries, it's not as well accepted as you might assume.
Okay, great. But here it is.
If you want to try and think of it as part of, you know how we talk about the sociocultural aspect of writing and their conventions and things? This is, the rounding up or down is a convention of this culture in the US and in the math environment that we've created. But that doesn't mean every culture has that same exact rounding convention.
Gotcha.
And believe it or not, that kind of process holds through a lot of science. We have this process, or this thing known as STP. STP stands for standard temperature and pressure. Okay? Because it's a standard, we would assume that our standard temperature is the same everywhere, right? Standard temperature and pressure, depending on who you talk to, a chemist, a physicist, or an engineer, is different. Okay? We still call it STP, but it's a different numerical value, depending on what they've decided was standard. Okay? And arguably, these standards of each of those situations aren't standard. For instance, chemistry's standard temperature is 0 degrees Celsius. Well, 0 degrees Celsius is what?
32 degrees Fahrenheit.
Ish.
32 degrees Fahrenheit, okay. That's a bunch of numbers. I don't know what numbers mean. What happens at 0 degrees Celsius? Water freezes. So chemists, as a standard, picked 0 degrees Celsius. Right? Engineers, as a standard, picked 22 degrees Celsius, or 25 typically. What is 25 degrees Celsius? It's room temperature. Which do you think would be a better standard?
Freezing point. Room temperature.
Most of your experiments are done at which temperature? Room temperature. What do you think is going to be a good standard temperature to use? Probably something closest to what we do all our experiments at. Right? That's why engineers picked room temperature, and why chemists unfortunately picked 0 degrees Celsius, because the calculations simplify with a 0 degree Celsius calculation. Right? Different standards for different environments, even though we still call them standards. Same thing can happen with rounding. Be aware, other places may not do 5 and up rounds. Our standard is, yes, 5 and up rounds up. What's the rounding down? What does this answer become? If it was 36.321? 36. It's not really rounding down, it's just not changing it. It's just leaving it alone. Right? Make sense? Right.
How did they determine, so how long ago did they choose that room temperature would be like a standard measure? Because, I mean, did that air conditioning back then or set room temperatures? Like, would it change with the seasons? Like, I don't understand how that's a scientific measurement. Whereas freezing point's the same around the world.
Yes, so you could run analysis in that respect. So for engineers, most engineers are designing their experiments or their systems to be within buildings, and buildings are climate controlled. So they can usually rely on that standard. Okay? Chemists say, well, depending on what room you're in, that doesn't make sense, and because everybody's room temperature is different, we're going to pick something that is now equally uncomfortable for everybody, and everybody has to convert, as opposed to just saying one person has to convert. Okay? And you might say, well, this doesn't make a big deal. My wife and I spent hours trying to figure out what the hell was going on with a piece of equipment she was using, because she could not get the correct flow rates coming out of her instrument. It turned out that the standard temperature and pressure that the engineers who built it used was room temperature, not 0 degrees. As soon as we made that substitute for our temperature, everything worked. And all they said was, yeah, we did it at STP. Yeah, thanks, guys. Okay. So we've got our rounding analysis. 5 and above, you round up. Okay. 5 and below, you leave it as is. Okay. Rounding, when should you round? You will always round your calculation at the very end. Notice when we did our first calculation up here, 0.75 plus 0.585. We didn't go into the calculator and say 0.75 plus 0.58. Okay? We aren't rounding the 0.585. We're only rounding the answer of the above calculation. Never round before your final answer. Okay? Which is unfortunately going to bring in another situation that becomes problematic. How many SigFigs are on our periodic table for the atomic weight? No, they are not infinite. I hear 4. So carbon, 112.01. That has 4 SigFigs. I agree. Good guess. Iridium. Iridium 77 has 5 SigFigs. Hydrogen, 3 SigFigs. Okay. What's the issue with using our periodic table for our SigFigs? Doesn't work. We get differing numbers of SigFigs on our periodic table. Okay? These aren't exact values. If I pull up a different periodic table, I can report out to the hundredths place. I can report out to the thousands place. Some of them can go out to the hundred thousandths place. We can continue to add significant digits onto each of those numbers. So how do we know what we should use when trying to use those numbers? How many SigFigs should we carry through? Okay. A couple things come out of it. Use the periodic table that you're given. Okay. Number 2, if it's a multiple choice test, hope to God your answer or whoever solved the question used the same periodic table. Okay. Is that always true? No. And when you go through and run calculations in your textbook based off of usually dealing with the elements, you may look at the answer in the back of the book and be like, well, I got the answer 1.23 and they got the answer 1.24. Well, they're different numbers, so I must have done something wrong. Unfortunately, usually what that's due to is rounding and what numbers did they use for their elements. Okay? So you have to be careful, particularly in chemistry, that sometimes you will get answers that are slightly off. That is usually a rounding error. If everything is done perfectly, you shouldn't encounter that rounding error. Okay? Very rarely do you ever do everything perfectly. Okay? And you will encounter that rounding error. Which means on an exam, because I'm cognizant of this, I don't say which is the correct answer, 1.24 or 1.23. Because I know what numbers you're using have a slight variance in them, and that might cause you to get to the wrong answer. Okay? So on a multiple choice, your multiple choice answers are different enough that it's not caused by rounding. Okay? That said, I am one of few instructors that watch out for that. Okay? I've encountered plenty of instructors that get nasty nitpicky on SigFigs and all of the rules on how we apply them. Okay? And then they themselves are inconsistent in how they apply those rules back to their own calculations. Okay? So you have to be very careful, particularly with online homework systems. Watch out for it. Be aware of it. Try not to punch your computer. Okay? We've got one big thing that we've done to fix that. Number 1, you have me as an instructor, so I don't ask that kind of question. And number 2, what's the online homework system we use? We don't. We don't have one. That's why we don't worry about it. Okay? Do you guys want to do a little practice?
Yes.
Okay. I'll give you 3 minutes to do a little practice. If you got questions about it, we report according to the least precise place. The first number goes to the thousands. Third place. There we go. I like that. The next number goes to the second decimal. Thousands, or a third, which means our answer needs to get reported to the second. I'm only allowed to say 129.04. That 1 has to disappear from my answer. Does that make sense?
Now, did you want the number of SigFigs in that answer, or did you want that answer?
I just wanted the answer reported to the proper number of SigFigs.
Okay.
Interesting observation. How many SigFigs do I have? 5. 3.09 has? 3. By doing that mathematical operation, I increase the number of SigFigs. Fair game. I'm allowed to do that. Okay, Dominic. Okay. We'll get to 5. Take a look at 4. Okay, and actually, we'll just kind of skip that out. For the answer, I believe you got, should have been 454. I don't know where you got 500 from. 0 meters cubed. Your calculator, I believe, actually spit out 38 dot something something something. We're only allowed 3 sig figs, 4, 5, and the 3. Because that 8 is larger than 5, I have to add 1. 4, 5, 4 is what a lot of students will write. This is now your paycheck. You just went from $4,500 to $454. Are you a little bit upset? Yeah. Sig figs do not change the meaning of the number. Okay, the meaning must stay the same. How can we make sure that that's 4,000? Throw in an insignificant 0. It is only insignificant because
There's no decimal point.
I do not define the decimal point.
Okay, so we do
Now I have the
apply
correct
that 0,
number.
though? You want us to-
You have to have that 0. Okay? Otherwise, it's 4,000 versus 400. You need the 0.
Is this where you come with, like, what you say was lead zeros and follow zeros or something like that?
Nope.
You were just talking about it.
Nope. That's not this case at all, unfortunately.
So Mike, are you saying if you like it, you should have put a ring on it?
No response. It was a box. The next one, your answer comes out to be 0.03, I don't know why I said grams, liters. You probably saw a bunch of other numbers strung out. Why can I only report it to that place? It's addition, subtraction. It's the least precise place, which is the second decimal point. I can only report it out to
Oh,
0.3.
that's what I got. I thought you were saying what we got from the calculator, though.
How did I get that number?
Like the first step, yeah.
I took 33.12 minus 33.0948 in the calculator.
No, but you do get 0.0252, so then you have to obviously get the least significant.
0.0252.
That's what I got, yeah.
Okay.
When I did it.
According to our calculation, we can only go to the hundredths
Yeah.
place, which is here.
I'm just saying, that's what I got for my answer, of course, the 0.03. I'm just saying, the first step is that.
I have to add 1 because of that rounded. That is a calculator that you can use,
Yes.
yeah. You just can't use a cell phone. Okay. And then the last one, kind of hard for me to see it. 0.0454. What units would I be using for this?
Grams of meters per centimeter.
Grams divided by centimeters cubed.
I did 45.4 times 10 to the third.
I haven't talked about powers of 10, so we don't even need to worry about it. It's probably equivalent. Okay, but then that works. We get our 3 sig figs. Make sense? That is our sig fig lesson for today. I talked way too long.